So very important, unsupervised learning. In the era of ChatGPT and such, so these types of networks and tools are kind of a little bit forgotten that they exist, but they do exist. And why they are important? Because they allow, I mean, if you just abstract away from the biological perspective that we do kind of unsupervised learning often, and this is one of the major mechanisms, learning mechanisms. Practically, unsupervised learning helps you to understand your data. So in addition to just kind of being part of more complex solutions, you can add on top, I don't know, reinforcement learning and such. But prior to all, it's one of the tools to see your data, to visualize it. And again, so as you understand, so from the point of visualization, so the principles are different compared to, for example, TSNE, if you used it before. But because it is really a kind of a learning-based mechanism rather than kind of statistics-based. Maybe a few more words about unsupervised learning or connected to SOM, just to kind of transition to the next topic. Except for SOM, so that's what Tatiana has presented yesterday. So this is the base architecture. So that's a kind of starting point for more advanced versions. There are even alternative interpretations of neurons while having same principles. So if you're interested, what you can do, let me see if I have it here. You can Google for something which is called elastic maps. So let me see, elastic map. Here it is. So that's also one of the popular learning techniques, very similar to self-organizing maps. In AI conferences, normally papers that deal with with the self-organized maps and elastic maps, they grouped in same sessions, and this technique was developed in the group in my home university originally a long time ago. And the idea here is that while in Cojonen's maps you have neurons, here instead of neurons you have you apply physics. So you change the elasticity between particles, and you kind of, depending on the data, you stretch the surface, or you bend it and really physically bend it, and you can visualize your data accordingly. So that thing to remember as an again one of the variants. Really, if you ask me personally, so it's always cool to visualize data. I mean, to understand how data points just play out in space. It gives you a lot of insights, even without classification. So if you have labels, you can overlay it and you can color it according to categories. That, of course, it gives even more information. But just understanding the shape of your points, so feature vectors, I always kind of, this is almost a recurrent message to you. Understand data as shapes, as manifolds in high-dimensional space, and this is one of the techniques, along with Cojonen maps, to somehow project this high dimensional space to some more tangible, easier to understand um, three-dimensional or two-dimensional cases. Another thing I want to demonstrate, I don't know, I don't remember, Tatiana, if you mentioned like growing some like variants. Interesting technique. Not that it is kind of mainstream or better than others. I just think it is interesting technique. I think most of the work with respect to algorithms appeared quite a long time ago, like 2010-ish, something like that. So another technique of interest I can name is growing some. Growing self-organizing maps, so there is even a Wikipedia. So this approach comes from the group where I'm affiliated as adjunct professor in Melbourne. And the idea, again, so if you remember, so now I just want to, again, you recollect what you heard about yesterday. So classical Kohonen maps or self-organizing maps assume a fixed lattice of neurons. So you try to fit all your data into this kind of restricted lattice, and it works, I mean, for many purposes. However, there are obvious limitations of this approach. I mean, so not all data can be projected just on 2D in this manner. So with this approach, which is called growing SOM or GSOM, you do not restrict yourself to specific size of neural lattice. Instead, you start with a small construct, maybe 3 nodes. So so 3 nodes in a row, or even a single node if you like, and you try to project all your data to the single node, or to some primitive lattice, maybe of this kind. And of course, you remember this mechanisms of choosing best matching unit and determining the neighborhood. So everything remains as previously, but then you at each iteration you try how well this structure fit your data. So you and essentially you compute the error. So you compute the distance, and you have a threshold on the distance for each sample. And then if for some samples, some feature vectors, the distance to any of the or to the best matching unit basically is higher than a threshold, predefined threshold. You say that, okay, so this map is no longer good for this. Yeah, you need to grow, and you basically fork so there are rules on how to fork this neurons. So you create new neurons, you create new lateral connections, and then you continue training on this new one. And then it's interesting that so of particular interest in machine learning or in AI. So let me see if do you write? No, I don't write anything yet. So of course, the most challenging cases are non-linearly separable. So, and there are some interesting data sets. So if you have an interest in machine learning or AI, so there are some synthetic data sets of non-linearly separable data. Like, for example, I showed one like circle in a circle, or one class within the other class, then some I don't know, star-shaped classes, classes like two rings going into a chain, and etc. And so the challenge is to, well, they used as benchmarks for to test different algorithms. So how well they are projected, separated, and etc. Oh, sorry. So what I mean here is that this growing sum can, it's interesting to see the patterns of how neurons are growing. So at the end, you have a kind of fractal structure where which repeats repeats or reflects the shapes of the classes that you analyze. So growing sum, interesting development. Then further on, you can you can think about something which is called concept drift. So that's something that we didn't talk about before. So it is an event when new data start to be, or a model start to be unfit to or outdated for a new data. So that's normally happens in reality. So if you build a model for analyzing tweets of different topics, so some new tweets on different topics obviously will be outliers. So, and there are different techniques on how to deal with concept drift, concept drift phenomenon. Connected to self-organizing maps. So another interesting development was something which is called cancel. So also from 2010, but again, the idea was interesting in the fact that so when you so the idea with the growing sum was that you create an arbitrary shape of your neural layout or topology, but at a certain point, and then the network converges. So you talked about convergence yesterday. So it's either number of iterations or again, so you check that the data in your training set fit to best matching units and a certain distance threshold. But again, so when you have this construct and you have and you define the threshold on how well data is fit, you can monitor that suddenly at some point this structure, so you have new samples that do not fit this data. And what to do next then? So if you have a substantial number or sufficient number of samples that are kind of outliers, you say, aha, so the current model is unfit, but what shall I do? Shall I just continue growing? And then, for example, here in this article, I think all of them are linked in Canvas. But the idea here is that no, we will do a new version of a kind of new news slice of a growing sum. So you keep the old one in the memory, and you start to build a completely new. So a new map by summarizing all the weights of the previous map in a single unit. So you can easily sum up. That's again, if you connect to what I told you about this hyperdimensional computing. I mean, in neural networks, in many cases, you see this move that some neural representations are summed up. So essentially, summing up neural representation can, I mean, you can think of it as a summary of a set of activations. So here is the same, and at the end, again, so now we are entering more of continual learning context. So you have versions of Zoom that are kind of reflects the progress, the evolution of your domain. Okay, that's it. Very important. Think that you can use it to analyze your data. Yes, but now I want to go into supervised learning again, and moreover, model-based supervised learning. Model-based supervised learning. Compare it to self-organizing maps. So we will do we will build a model, but a model not a model of a separator, but a rather model of a class representation. So what do I mean with this? Well, at the end, so the separation will be between classes will be explicitly or implicitly defined. So you have your feature vector X, and basically here you have your features x1, xn, and you. So now when I draw it, so don't put any particular semantic into it. So you give a weight to each of the features. And then you implement a function. And again, let's call it a function that is being activated by or being activated or computed as a result of input variables. So this is a function computed for input x. Computed or again, so let's use this term activated. Already, and let's put it as f act here. So I deliberately not to introduce, not to tell about the circle as a neuron or something. So this is a function. So in the simplest case, it can be a sum. It can be any other function. So, and this is also I do on purpose because I mean, in what follows, I will talk about feed-forward artificial neural networks. But those neural networks, it's you should see it as a complex function. So it is only inspired by biological neurons. So it is, I mean, as far from biological neurons as one can only imagine. But similar behavior was, of course, observed a long time ago during 40s, that biological neurons somehow are connected to other neurons, and they react on the pulses, so they become activated. So I mean, it is a model of a biological neuron. Mathematically, so if you put some into this f, so you will have so the result of this function would be and you computed for a selected category of feature vectors, so for a single class. And then you will have a weighted sum, basically, of all items corresponding, which will produce a score that a given sample belongs to a certain category. So basically, in this model, a category or a class is modeled as basically sum or as weighted sum of features. So the ground model, so the basic model then for a score. So let's define this as a, so that will be our score. Class 1. Yes.
Would you like to move the...
Oh, yes, of course, yes. So you can do it like this. So it's some function, and then we put a weighted sum of features. And again, so far, so that so this model is very natural, so to say. You assume that feature vectors which characterize a certain category, they are approximately the same. Well, they have something in common. So what you do, you create a model for this class as a weighted sum of features. So that's your initial assumption. And then later on, so we will generalize this function. So we will fill it with some content. So, but so this is our starting model. But now we want to somehow choose the weights of the feature vectors that kind of move the score, make the score for a given category higher than for other categories. So, and in a way, the score will be improved by correcting errors. And that makes this class of neural networks defined as error correcting neural networks. So that was competitive neural networks you talked about yesterday. This will be error correcting. So neural networks with error correcting learning. So to do that, so to implement error correcting learning, so you have your score function, which is act xi. Oh, you need to be able to well, you need to have two things. You need to evaluate how well how good your score is, and secondly, you want to observe. You want to check how the score is sensitive to the change of weights. So how changing a single weight or each and every weight will result in the change of y. So we first talk about the second part. And then, of course, I mean, you can reasonably notice that I omitted a free term there, but I mean, it doesn't really matter for the discussion at this point. So let's focus first on the second item. So, evaluate mechanism. So here we should dive deep into our memories and retrieve knowledge from gymnasium about derivatives. So because derivatives are essentially measures of sensitivity of function to change of parameters. So again, if you have your function f of x, and this is x, and so you have something like this. So you have, boom, here you have x, and then you have some step x plus h, yeah, so what you are up to is to see, so, and this is f of x, and this is f of x plus h. So so your f of x dh, what dh is h f of x divided by h. Yeah, and here, of course, it's a limit when h goes to 0. So, and that's you also remember that it's this is your delta f, this thing. So this is your h. Yeah, that's the thing. This is your h, and this is your alpha. So basically, it tells you how the change in one parameter is how a particular function changes, reacts on changes in the input parameter. Yes. So basically, this tangent of alpha is a measure of sensitivity. So obviously. Right? So it means that we will we need to compute derivatives of something of certain function to understand how well or how it reacts on changes in weights. But what is this function? So score. So score is just a score. So it's just a number. So you sum up your features, do weighted sum of features for a given vector, and you have a number. So you want to evaluate it. And for this, you need to introduce this new function, which is a goodness or cost function. So cost, well, which is a measure of quality of a score. And again, so let's use this common notation. So in J, so it will be a function of output score of your model. And a desired outcome. Well, presented in this form, this J can be anything, as you understand. But again, so you need to somehow find a way to interpret score in terms of the desired outcome. And what is the desired outcome in supervised learning? Is that the model actually produces a prediction on a category, and categories are marked with labels. So in the binary classification case of SVM, so the trick or the it's not a trick. It was a very nice move to assign a number, really an integer number, to a positive class, like +1, and -1 to a negative class. So here, I mean, we are talking about classification, a multi-class classification. So we need to find other ways of encoding classes. And so a typical way of encoding, so really, I mean, or representing desired outcome is to have a vector of categories. So you have at the end you have a vector of categories. So C which will contain labels CN. So or let's put it C classes. So it's number of classes. Again, here can be probably different ways of doing that. One of the conventional ways for encoding classes is, as you may guess, is what? Something which is called one-hot encoding. One-hot meaning that you have a vector, and to denote a specific a class to which specific sample belongs to, you put 1 in the position of that class. How biologically plausible is that? That is a big question. I mean, you probably heard, I mean, there are some evidences about a special type of neurons or small groups of neurons, really small groups of neurons that activated just on specific phenomena. So they're called like mother cells or Jennifer Lopez cell or whatever. So inside the brain, we have some regions that kind of react on very strong categories, but in general, not. So neurons are not specific to categories. So, and that's what I'm saying. I mean, what I'm presenting you as an artificial neural network is rather an artificial mathematical construct. So we want to somehow denote categories, and it's just convenient for us to encode it as using one-hot encoding, putting 1 in a position of true class. So all our labels, cats, dogs, airplanes, you name it, at the end, all will be listed and to form a class or category vector. And for a given sample, a one-hot encoding will be applied to produce the desired output of the model. But then again, so the key word here is a vector. It is a vector. Well, it is a vector of dimensionalities number of classes with all zeros but one position. And so this is the desired outcome. And then I just want to remind you that our base model. So we have our feature vector x, and we have so we decided to have act. So that is weighted sum function, some function of a weighted sum of this axis x1, xn, and is the dimensionality of the feature vector v1, vn, and we say that this guy over here produces a score. And then, of course, that was introduced for a single category. So if we have more categories, so we have many of such, or as many as act, score, class 1, C1, score, the class. Acting exactly on the same inputs, but with the different weights, of course. I mean, so we need to introduce extra indices here. So this is for 1, and that will be wn for a class plus. So actually, I mean, you can be happy with this construct. So you have some scores for a given input. So you have n pieces of functions computing a score. Not n, the number corresponding to the number of classes. And on the other hand, you have this C vector, C1, C class. So you can compare them, these two things. So you have a vector on the one hand, so this is a vector of scores. And the target vector. So you want this course to be the target vector somehow. So you need to decide are those good scores. So with respect to something which is called ground truth. So this is a supervised learning. So this is your ground truth. And so, and that's why so you need an extra function J. So J that takes the scores on the one hand, takes the desired outcome as one-hot encoder, let me just denote here is so these are the one-hot encoder vectors. Single hot. Yes. Okay. So you need to take the desired outcome, you need to take the actual outcome and compare them. So what are the options here? Again, if you would design it, such a system, what can you do? I mean, the simplest possible solution. Subtracting. What would it correspond to? A Manhattan distance. So you need to compute a distance, a measure. So there are, and as we learned, so there are plenty of options in principle. So again, don't get stuck on the word distance at this point. I'm just saying that that's the correct way of thinking. But again, let this subtraction not divert you from or not divert you to a wrong mental path in lab 2, for example, because there is also subtraction, but as I mean, it's a different one, as we will see a little bit later. So yes, you need to compute the distance. So this cost function is a distance function. And it is this function that we want to optimize or to minimize. So we want to minimize the distance, the error. So when I say distance, error, cost, so these are all synonyms in this context. So larger distance means larger error. So it means that the predictions are far away from the desired outcome. So at the end, we need to compute. We need to minimize J. So if we have a single, if we take just a single score, oops, I'm sorry. Well, yes. So if we have our output, just act or half of act of x. So now it's a vector form. So essentially, to do that, we take dj, and our j is a function of f act x and the ground truth. And we computed with respect to each and every weight. And that is why you see partial derivative. So you compute the partial derivative with respect to each and every weight. And with these, again, so the meaning is that you try how this function and everything which is included as parameters is sensitive to the tuning of a particular weight. And then the learning itself is rather simple. You saw it already. You saw an instance of it in SOM somehow, but in a slightly different form. But you recognize it. So at the end, your optimization is about computing a new weights such that they adjusted by this value. And then, of course, already yesterday, so you introduced this hyperparameter, which is a learning rate. I mean, so you don't, I mean, that comes from numerical methods. So you don't want to make big steps. So you do kind of very careful adjustments with respect to gradient. So this is a gradient. And the minus corresponds to opposite trend, basically. So this is a trend. So what I introduced so far is just the conceptual idea. What we need to make our model-based or a data-driven model of a class trainable. So the training principle. And now I just want to add some more properties to it. So first, J of, and now we use this notation of y hat y. So y is of predictions, and this is the true labels. Hot. So in order to do that, this type of learning, so obviously this thing needs to be differentiable. And what you do, you compute gradients. Gradients. And implement learning. So now I make a big jump. So let me see how I do. Maybe we can make a couple of minutes break before just to. So 2 minutes. All right, so let's continue it. Yes, two things. Where is it? Yeah, I want to bring up this figure again. Generalist model. So we started off with the following formulation. So we have x, which is x1, blah, blah, blah. So, and then we have act. So I introduce them as scores. And then we have this kind of input. So the general formulation tells that we do not compute, although we can live with this kind of shallow structure, but in a general form we have other activation function. So we build a nested structure. Act. So here we have our own set of weights, and which at the end of act score. So this is our scores. Basically, looking at this construct, what can you say? So why do we need it? Or what do we do, essentially? So before I introduce the single, so we started with saying, okay, so we model a certain category as weighted sum or a function acting on a weighted sum of inputs for a single category. So I introduced only this part. And so we create as many models as for scores as number of classes. So and again, essentially at this point, so the word neurons or neurals are rather irrelevant. So we just decided that we build a model in this form. And essentially, what we want to have a function that maps our feature vector to another vector. A transform. So from one coordinate system to another coordinate system. And as you imagine, so that transform is not obvious at all. I mean, so you cannot, come up with a single analytic equation. So that isn't feasible. So because this function is complex. So so what we do here, I mean, even with the first step, we try to approximate this function. And that maps one vector to another vector. And apparently, again, maybe for very simple constructs like I don't even want to some OR function if you want to learn OR function. So I mean you can get away with rather simple constructs. Already for learning XOR function, you need a single neuron is not sufficient. So what you want to build an approximator of a complex function, and but you do it in a kind of piecewise manner. So at the end, the whole what you see here graphically is a network of some standard and simple atomic functions that together approximate this function that maps from one vector space to another vector space. And that is also why you should remember that feed-forward artificial neural networks are also regarded as universal approximators. So they can approximate any function. And again, that's a purely mathematical construct. So you just want to approximate the function, and if you recall, so some functions can be approximated by piecewise linear method. Some functions, so there are different other methods to approximation. So this is just a method to approximate any function. And then the more complex function, if you have a more complex function, so it will be reflected in the structure of your network, of your computational graph. Then you see very silent here. I would expect a question about how many these computational units you need. So that's a big magic. You need quite a lot of them, and then so there are also connections to our discussion on high-dimensional representation. So, for example, typically the first step you want to project your original vector representation to high dimensional representation. So first layer is a projection layer. So you can interpret also, so looking at this structure, you also can interpret transformation of vector into spaces, vector spaces of different dimensionalities. As you know, if you are interested in machine learning, so there are different shapes of networks. So you can find more trapeze-like architectures, U architectures, and such. But in all cases, so these architectures reflect different ways of modifying the vector representations of the original vector so that it comes closer to the desired vector representation. Yes, but now we didn't talk much about the content of these functions, f and scores and j. So we talked about difference, yes. But again, purely from the mathematical formulation, so there are several things we need to do. We needed to be differential, so on the one hand, and secondly, these functions. So, well, while saying that they're kind of atomic and simple, so they shouldn't be linear. So, I mean, we talk about, as I said, complex case with where linear combination, or which you cannot build this approximator by linear approximation of these vector transformations. So these functions should be nonlinear and differentiable. And there are different ones which was suggested. So several options for act. So, and then let's discuss also why. So first, you can tell me. So what first comes to mind? Huh? What did you say? ReLU. Okay, let's start. Let's start with ReL, which stands for rectified linear unit. Really, so it looks like this. So if you have your x, and this is ReL of x, so it looks like this. So for all negative values of x, it becomes 0, and so essentially ReLU of x is a max of 0 and x. So that's the definition. And so let's also write down the derivative. So d ReLU dx is, so I will not torture you with this math, 0 and 1 for x so for 0 and for x, right? Sorry, for minus x, for negative x. Interesting. I'll tell you why it is interesting. Next, two, just to quickly fill in. So we have a sigmoid. Sigmoid looks like this. So we have, again, X, sigmoid. It is normally denoted as this, sigmoid. So it is bounded by 1, and it goes like this, smooth, like goes 2.5. So so this is 0, and it is defined as x 1 over 1 plus e minus x. And the interesting thing is that d sigma dx is a sigma multiplied by 1 minus sigma. So you can check it yourself. And finally, we have something which is called hyperbolic tangents. So which looks like this. So it's from -1 to 1. And is defined as ex minus e minus x divided by e to the power of x plus e to the power of minus x. And they so d tan h dx equals to 1 minus tan h squared of x. So the question is why I mean this functions was chosen in this way. Well, I guess I think again, so there is a purely mathematical explanation. So we need a nonlinear bounded function. So and this functions was known as since before, and also I guess that due to the specific way of computing the derivative. So basically, the derivative can be computed from the function itself. So, so you don't. So once computing the function, so you already know how to compute the derivative. Also, when looking at this things, you probably should notice, and I linked one document in Canvas. The need for now it becomes more evident why you need to do pre-processing of your data. So your data need to be relevant to these functions. So, for example, if your data is all positive, so basically this function will not work at all. I mean, it will simply pass through any value. So the meaning with nonlinearity is that you selectively you make these functions to selectively react on input. So because otherwise it will be just linear. And as we discussed, so the complexity of the underlying phenomena is so high that you I mean cannot get away with linear stuff. Same goes for other two functions. I also want to add that there is a great deal of research. I mean, if you talk about acceleration of neural networks, is how to approximate these functions using more computationally simple primitives, because here we have exponentiation, which is an expensive operation. So one of the directions to speed it up is to, for example, approximate these functions as a set of quadratic functions, for example. So you do approximations on them themselves. Right. Now, for the rest of discussion, so we now filled in the content of this activation function. Maybe I want I at least find for myself rather difficult to do computations or do thinking about this complex network structure. So what we do now, and maybe so I will augment this slide. So I will select a single single chain of it. So again, we go back to our original formulation. So at the end, we want to compute score from the input, but now wide chain of activation functions, or a network of activation functions. So what we do, and now we understood that these Fs are activation function, nonlinear activation functions. So at the end, if we just use whatever functions I introduced, so the ReLU, sigmoid, and such, they will speed out a score. Well, depending on the function, in the range from either 1 minus 1 1, 0 1, or well 0 whatever magnitude you have in your data. So if you approach normally, so I think you also limit it, normalize it and do Z transform. So it's also between 0 and 1. And as we discussed previously, so you can try computing a distance. But then what you need to do again, so now just make it mentally. So take a simple difference as you suggested. So what does it mean? So you have a difference. And you need to take a derivative of this function with respect to w's. So and you can try it yourself for this for a simple. So if you assume that your cost function is a simple difference, you can try to compute a derivative of this function with respect to scores. And see the resulting equations. Now I kind of do the next jump, so to say, to what is used mostly as a cost function, and I will explain you briefly. I mean, the reason for this function purely from mathematical perspective. So at the end, you want so you want to find such a distance that that the derivative is also computationally simple. And then again, so it just happened through the years of research on neural networks that somebody understood that the scores in the way that would be produced by these activation functions, they need to be further normalized, so to say, so across each other. And then, so one of the ideas was to make to make the output, I mean the whole vector, looking more as probabilities. So because at the end we want to match it to one-hot encoding, so we want to have a kind of clear indication from the score function which of the n classes is most probable. So what was decided to do is to do two things. So first, you want probabilistic interpretation. Of scores. So you can check yourself that if you have computed scores using one of these functions, so I mean, they don't fit the definitions of probabilities. And what are the definitions of probabilities? Well, they're between 0 and 1, and they all sum up to 1. So here you don't control that sum of scores equals to 1. So, so scores are more or less independently computed. And secondly, if you have probabilistic interpretation of your scores, so you need to choose appropriate measure of a distance. So simple difference wouldn't work here in this case. Again, so if you assume that your output are probabilities, so you need to choose correct measures. The distributions. So, and these are two distinct steps that actually add final bits to our architecture. So let's consider the output layer. So we have our x, x1, 10. So we have our activation functions. Then we have our scores. So we have our scores. So what we want to make them as probabilities, and we do it using something which is called softmax normalization. softmax S of X, and which outputs the probabilities P1, P3, L. So softmax converts scores into probabilities in the following way. So it takes S of xi, or a score. And do it like this. So it's x e to the power x. Oh, let it be x here. Just for brevity. Xi. And you normalize it. Sum of e x I j for j1, 2 classes. So this is your cost function. And then, long story short, so the derivative of this, so the derivative d, or partial derivative ds on dx. So it has a form, well, depending on which x it is. So it's either s of s1 minus s, or so dxk, and or minus s multiplied by s of x j multiplied by s of xk for k j, and this is for j. So this is the derivative of it. So the final piece. So if you have the output layer interpreted as probability, so they all sum up to 1 and between 0 and 1. So the measure of distance between probabilities is something which is known as cross entropy. As distance. So I just want to write one equation, x hc b. I will tell you what this is now, equals minus sum ci logarithm pi plus, so that's the thing, 1 minus ci logarithm 1 minus pi. So to understand this, you need to go to dive deeper into information theory and understand the entropy stuff. But this is your measure of distance. A rather complicated thing. So I did an effort to take a derivative of this guy with respect to softmax, and at the end, what you want. At the end, what you want, I will just complement the figure here. So here you have your cross entropy as J. So which takes, I mean, these probabilities as input and truth. So one hot and so the 0, 0, 1, 0. So one hot encoded truth. And you want to compare the distributions. So there's one hot encoded, so that's one distribution, and the resulting and the output of the network. And but at the end, what you want to compute, and this is your error, so the or cost that you want to minimize. So error E. So the optimization nice H or minimize. H with respect to weights that are in-baked in this piece. And as you look at this diagram, so what you want to compute, so you want to compute the derivative of this function with respect to weights which are hidden here somewhere. And to do that, you first compute dH by d scores and pass it through and these scores are you get to it via softmax function. So by chain rule. Again, I suggest you do the calculations yourself. So you basically take a derivative of that, expand D as a softmax, and within softmax you take so you express the scores, and at the end, this thing over here, so the first level derivative, what you will see is it will be pi a minus c I. So which is essentially are your predictors. No, so y hat, and this is your true vector y. So what you see in the lab, so now I tell it in clear. So the idea of with the backpropagation lab is to understand different pieces in the implementation. So at some point, you will be asked to interpret a line where you see a difference. And that's, remember that, I mean, you clearly see a difference taken between the predicted labels computed on the forward path and the output. And when you see it there, so it shouldn't be mistaken for a cost function. It is not. It is a derivative of a cost function with respect to scores. And so you will be asked what cost function it is used. But again, I encourage you to take this. It will take you like 3-5 pages of calculations to come up with these results when taking this derivative in analytical form. So with all these exponentiations and logarithms and such. So that's it from me. Any questions? No. Okay, good. Thank you.